Okay. So let us start. So our goal for today is to prove the following theorem. Suppose x is a log concave random vector and isotropic on Rn. And recall isotropic means covariance identity and centered. Then okay, the expectation of the covariance of x condition of x plus square root s g and the norm, this is less than some constant, and this is true for every s larger than some constant log n square, where G is standard Gaussian, independent of x. Okay, this is our goal for today. Maybe let me recall why we want this. This morning, Boaz showed us that if S naught is such that x plus s, sorry, square root sg. Okay, less than c for all s bigger than s naught. Okay, so if you happen to have this information, then, sorry, so if x is log concave, so if x log concave, and you happen to know this, then the Poincaré constant of x is less than some constant times s naught. Yeah, something is wrong. So it was. Yes, square root of s naught. Okay. So this he proved. So I don't do it. So he kind of made a mess of the proof, right? No. No. Okay. Okay, so this was, this was this argument decomposition of variant. You start. I just give you like the start. You do var f of x is expectation var f of x condition on x plus s plus variant expectation f(x) on x plus s, and it turns out that he showed you like that this term like is somehow you can. What did I do? No, it's fine. You can control this term by this one somehow. And then you get, I don't remember exactly, maybe 2 plus Cp of mu divided by S times this one. Sorry, it's square root Sg. And then there was, here the argument was that this guy is like uniformly log concave, or 1 over s uniformly log concave. You use the improved Lichner-Ovitz, and then you get, so you get 2 plus Cp of mu s times expectation the covariance of this thing half divided by square root s. And you just upper bound the gradient by the Lipschitz function, the Lipschitz constant of f. And then so you get this you can assume to be 1. And you use Emmanuel Millman, and then you see that you get sorry? Yeah, okay, I got confused. Yeah, it's. Yeah, sorry. And what happens is that so you get 2 square root of s plus Cp of mu divided by square root of s. And by Emmanuel Millman, you can take the worst function. So you get this for every s larger than s naught. Okay, and this clearly implies this. Okay, so to prove the theorem, we will reverse time, as I said. T is 1 over s. Okay, and so the conditional law of x given x plus at least in law is a stochastic localization. Mu t. So the theorem amounts to the following. So I'm just rewriting the theorem, but with this language. Okay, if mu is log concave and isotropic. This is just the same theorem. The expectation of the covariance of mu t is order 1 for t about log n square. So this is the goal. The advantage of reversing time is that we can use like some formula for the derivative of mu a long time and for the derivative of its covariance, and this is what we will. Mm-hmm.
So is this first theorem for any g, or
there is such for any g? No, g is fixed. It's g is this script n stands for normal, so it's a Gaussian, standard Gaussian. Okay, so there will be many steps. It's kind of a long process, but somehow I make you a promise that taken individually, all the steps are somewhat easy. Okay. Maybe what I should start with is like the equation for the covariance of mu t. So recall so that if so mu t is a martingale. So when you start with some test function, the martingale. So recall that for any test function, and somehow the derivative, the Ito derivative of this martingale. So this is, you remember I call this the moment generating property. Where so this is the Barry center. Okay, so for any f, for any reasonable function f. Okay, so for instance, so if f of x equals xi, you get d of xi d mu t equals integral xi x minus at d mu t dwt equals integral x minus at I x minus at mu t dwt, which is the covariance of mu t applied to vector ei and dot with dwt, and the ith coordinate vector. So if you and this is and this is dAt I, if you want. So you see that dAt is At dwt, where I will give a name to this covariance, where At is this covariance. Okay, so far so good. And we can apply to the same principle to, f of x equals xi xj, like some quadratic form, so on likewise. And you get the following. Lemma. dAt. So it's a random matrix. You will get sum equals up to n integral x minus at I x minus at try d mu t dwi. So this is just the ith coordinate of my Brownian motion. And this is the martingale term, and there is like some term that comes from the Ito derivative, because, okay, At is integral x tensor x d mu t minus 80 tensor 80, okay? And from this term here, you will have some dt part. And it's 80 squared dt. So somehow, I want to upper bound 80, so this part will only be helping me, okay? Because it's something. 80 is a covariance, so it's a positive matrix, so 80 square, it's a symmetric matrix, so 80 square is a positive matrix, so this is something that goes down. Actually, it won't help me much. It just I will throw it away. I mean, the proof is an exercise. I leave the proof as an exercise. Okay, the details. Okay. So that's my equation for 80. So 80 is it's a random matrix. So it's a random process taking the value in matrices. I have an equation for this, and like the issue is that I want to control the operator norm, and the operator norm is some function that is not smooth for matrices. So I have issues. So I will use a proxy for operator norm. This is something very classical in random matrix theory, that if you want to bound the operator norm of some random matrix, you could look at the trace of some power instead, or the log of the trace of the exponential of the matrix, or something like that, okay? So I will need some matrix inequalities. So maybe this second part, some matrix inequalities. So lemma. Let I don't know, K, H symmetric matrices. Okay, what do I need? Okay, alpha beta positive. And I'm assuming one of the two is non-negative. Yes. K. Yes. K positive. So this for matrix it means okay, in the sense of being PSD. So okay. Non-negative eigenvalues. So trace K to the alpha H, K beta H, less trace K alpha plus beta H square. Okay? No. Yeah, exercise. Lemma. So the second lemma, so let phi of a symmetric matrix be the trace of exponential of m. Then for every m H symmetric, the Hessian of phi at m H Okay, so this is the Hessian of phi. I look at this as like a bilinear form on the set of matrices. Okay. So it's smaller than grad phi, then apply it to h square, which is trace em h square. Okay, proof. Should that be an exercise also? Because for sure, if I try to make it, I will mess it up. But okay, maybe I can try. I have my notes. Okay, I expand everything in power series, and I will get some. Okay, one sum. Trace, so there will be something like aim k minus l h m l h maybe L goes to so maybe it's k minus 1 minus L. Okay, I wrote this formula on my notes. I hope it's correct. I think you expand phi m h like a power series, and then this is what you get for the second order term. Okay, assume m is positive. Then you apply the first lemma. You get less, so this is less than sum k 1 over k minus 1 times k minus 1 trace h k minus 1 oh, something is wrong. Okay, I knew I would make a mess of it, but yeah, okay, no. This was 1 over k, sorry. And here is the k, because after all this term, I still don't know the number of terms when you use this. So it's k, not k minus 1. And well, yeah, make my m's and h, they look alike, which doesn't help. And this is trace e to the m h square, which does the trick when m is positive. But actually, you can assume m is positive.
So you can just repeat how you define the gradient?
Sorry? This is the gradient. So this is so I'm looking at this function phi from symmetric matrices. 2R. Okay, so this is a vector space. So this is the second differential, and this is like, yeah, okay. Usually the gradient is the adjoint. Okay, I'm being imprecise. So here maybe I meant the dot product between h square and the gradient, which means the trace gradient h squared, because on symmetric matrices the scalar product is just a straight through the product. Maybe that was the question, right? Okay. And Okay, and actually, so I had to assume m is positive. But since phi of m plus lambda times identity is E lambda phi of m, I can assume that m is positive by adding a sufficiently large multiple of identity to it. Yeah, of course. Yeah, if phi has this property, also the derivatives of phi have this property. Okay, that's all for matrices, I think. What do I need? Okay. Okay, now start the fun part. Inequalities for 3 tensors. Do I still have the equation for A? Yes, I have the equation for A. So you see, so I said like there is this moment generating property. So when I differentiate A, I have 3 tensors. Okay? Because integral x tensor 3 times. Okay, so I need to control these kind of things, right? So one thing that is nice is that recall that AT is the barycenter of mu. Okay, so the vector that is inside the integral with respect to mu t here is something centered. Okay, the AT centers my measure. Okay. So I need 2 lemmas. Okay, lemma 1. Okay, x centered log concave. So centered just means E of x equals 0. Let U a unit vector, deterministic. Now, the kind of thing that I want to control is x dot u, x tensor x, and then the norm of this. Okay, I claim this is less and up to a constant than the covariance of x. And probably there should be some power, because this is not homogeneous, 3/2. Is there a problem? No? Okay, proof. Okay, so set HU equals so H sub U. So let me compute H sub U V dot V. So that expectation X dot U X dot V square, Cauchy-Schwarz. And now I use log concavity. So you can compare moments for log concavity. So x dot v will be a log concave random variable. And we've seen several times in Boas talk that for log concave random variables, you can compare moments. Like you have some inverse holder. Inverse holder for log concave random variables. And so that's not half, okay. And so that's less than, okay. Each of these terms is less than the operator norm of the covariance. Next, yeah, up to a constant. So far, so good. And lemma 2 in the same spirit. Something of its flavor. So, except that here I don't need log concave. I will, and then I claim that if I look at this matrix, no, hang on. Yes, it's kind of a mess. Sum x tensor 2. Then I take a square. The square is outside the expectation, okay? It will be clear like that. And it's less than okay. Proof. Okay, so set hi equals then fix u vector, deterministic vector of norm 1. Then I will look at sum hi square u dot u. And after some computation, which I'll skip, you see that this is the same as trace h of u square. I'll skip some details, like it's. But this is just some algebraic manipulation where h sub u okay, the same notation as here. Okay, so I want to upper bound h of u square. So this is expectation h of u. Okay, so we trace, okay, this is trace h of u, and one of the h of u's, I replace it by its definition. Then I do Cauchy-Schwarz. This is the only inequality I know. Except that I know it a fancy version. that was used several times, that the vector is centered, okay? Ex is 0, so I can subtract a constant, okay? So in Cauchy-Schwarz, I can put, wait, no, sorry. This one is centered, so I can subtract a constant to this one. Now I use Poincaré, okay? I'm assuming, yeah, I didn't say, but Poincaré constant. Okay, maybe this term I upper bound by the operator norm of the covariance, okay? That's of x maybe to the 1/2. The Poincaré constant, so there will be a 1/2 times the gradient, the expectation of the gradient square of this map.
So is the equality above the one in the face? The second equality in the line that starts with trace.
Ah, sorry, this was tensor 2. I claimed I trace. This is a permutation of the trace, like this. How would you call it? Yeah, this U, I put it here. Yeah, there is some linear algebra. It's fun. Okay, what is the gradient? Analysis 2. What is the gradient of HUX dot x? It's 2HUX, okay? Right? And then I take the Euclidean norm of the gradient. And maybe there was a half. Okay, so trace HU squared is less than 4. Who cares about the constant? And now, expectation HUX squared is trace HU covariance of x. And there was this 1/2, and I lost the Poincaré constant in the middle. So this is less than, this trace, I will upper bound it by the trace of H times the operator norm of the covariance. Sorry. Mistake. Yeah, you can interrupt when I make mistakes. Yeah, so it's expectation A x square, it's trace A square covariance of x. Okay? Okay, so this less than 4. Correct the operator norm. So there will be 1/2 from here and 1/2 from here. So 1. 1/2. X 1/2. Okay, so if you cancel out, so we get, yeah, this was a 2, sorry. But anyway, I don't care about constant, so. Okay, which is the result. Okay, so far so good. Here I should make a remark. We only applied Poincaré to a quadratic form. So here I was a bit wasteful. I was willing to pay the full Poincaré constants, and I only applied Poincaré to some quadratic forms, so I could say like introduce some Poincaré constant of quadratic forms. But somehow I won't need this remark here. Let me just mention that this remark was key in the original work of Eldon. Okay, that here at this stage I only apply Poincaré to a quadratic form. I think that's all for 3 tensors. Now we need a bit of probability. Something that I will call Friedman inequality. Some sort of relatively classical thing for martingales. I don't know, let me put it as a lemma. So MT continuous martingale. Okay, all my martingales are continuous. So some Ito process, if you want. Then, starting from 0, and then it's a deviation inequality, which takes this form. Then the probability that there exists T positive such that MT is larger than U and the quadratic variation is less than sigma square is less or equal than exponential minus U square over 2 sigma square. And this is valid for every U positive. Okay, this is called Friedman inequality. Proof, maybe I won't do all the details. Yeah, let's prove just a simpler statement. Start with a simpler statement. So assume that MT is less than sigma square, almost surely. Then, for every U, the probability that MT is less than U, is larger than U, sorry, is smaller than, so the same conclusion. And this is sort of easy because indeed exp for any parameter theta, x theta mt minus theta square mt over 2, sorry, is always super martingale. So super martingale, yeah, this, yeah, the terms are kind of confusing. Super martingale is something that decreases, like up. Well, actually, yeah. Okay, well, whatever. Yeah, actually, it's even in this situation, it's even a martingale. I could remove this word, but I don't know. Okay, who cares? In particular, expectation exponential theta mt minus theta square over 2 mt is always smaller than e theta 0 equals 1. So if mt is less than sigma square, then, so if in addition, you know, you have this information, you get e theta mt less than x theta square the square over 2, and then use Chernoff, and disprove the Chernoff. U is in Chernoff.
Yes, but we haven't got this U.
I don't know. What I call Chernoff is Markov to exponential. Ah, pardon. Merci. So what I call Chernoff is you apply Markov inequality to E theta mt and then optimize in theta. Some people call this Chernoff. I don't know. Okay, for the full statement, I won't give you the details, but so for the full Friedman inequality, introduce the stopping time let me call it tau, which is inf t positive such that m t exceeds or equals sigma square, and apply the simpler statement simpler version to the martingale stopped at time tau. I'll let you fill in the details. Okay, so good. So far, so good. I think I'm done with the preliminaries. Okay, so I can prove the theorem, I think, now. Okay, I will prove some kind of a refined version. Okay, I will prove. So under the same the hypothesis, so assume mu log concave isotropic. Okay. So there is a universal constant such that okay, so mu t is the localization and AT is the covariance of mu t. Okay, now the statement is the following. The probability that there exists S less than T such that AS is larger than 2, say, is less or equal than exp minus 1 over C T. And this is true provided T is less than 1 over C log n square. Maybe before proving this, let me explain why this implies the bound on the expectation of AT. Because here you see I only, in particular, I have a bound for the probability that AT is larger than 2. Provided T is in this range. But okay, why do I have a bound for the expectation of IT? Why just a deviation for the probability that being larger than 2 is enough? The reason is that I have also an almost sure information about the norm of AT. Okay. Okay, so maybe proof that this implies theorem 1. This is actually very easy, this part. Recall that as mu t is t uniformly log concave, we have the covariance is less than 1 over t, almost one. So the expectation of AT is less than 1 over t times the probability that AT is larger than 2 plus 2. Okay? I mean, you just split this expectation under the event that AT is larger than 2 and the event that AT is smaller than 2. And if t is in the correct time range, this is at most e to the minus 1 over t e to the minus ct plus 2. And this 1 over t e to the minus 1 over t is a bounded function. Okay, so this is O of 1. Well, so you see that this deviation bound is kind of an overkill for what I want. For instance, from this statement and with the same proof, I could give you a bound on any moment of the norm of AT. Okay. For what it's worth. The reason why I like to prove this estimate is that this estimate is almost sharp. Actually, it's, maybe I'll have time to say a few words about this. Yeah, I think I will make a break now. 10 minutes break. I don't know if it's a good strategy or not.